Today's video is focused on in class 7, which is the second day of notes for standard number 2, all about angles. In our introduction today, we have been tasked with finding the measurement of several missing angles. And so if we think back to yesterday's notes with in class 6, I'm noticing a straight line, actually two straight lines, that are intersecting in these diagrams. So if we think about our linear pair theorem, yesterday we learned that these two angles should add up to be a total of 180 degrees. So if 65 degrees is the measure of angle AEB, we should be able to find the adjacent angle that forms that straight line, the measure of angle BEC, by doing a quick subtraction from 180 degrees. So this angle here would be 115 degrees. A similar thing will happen if we focus on the other straight line in the picture. So again, the measure of angle BEA is 65 degrees, and then this adjacent angle would have a measure from A to E to D, also of 115 degrees, to make that total 180. And if we rotate back to the first line that we used, we can use this 115 degree angle we just found, which would be adjacent to this last angle here, angle CED. So the measure of angle CED would be 180 minus 115, which takes us back to 65 degrees. A similar situation is going to happen here in example B. So if we look at this straight line, we would be able to add these two angles together to equal 180 degrees. 180 minus 95 leaves 85 degrees left over. And we rotate to another line. The same situation happens with these two adjacent angles. So subtracting from 180 would give us 95. And if we do that one more time, either with these two angles or these two angles, subtracting 95 from 180 would give us 85 degrees. So all of that work is based on what we've learned previously is called linear pair theorem. We just use that idea over and over and over again. But what ends up happening is it actually brings up another idea that we can use to solve problems as well. So if we look at these two angles across from each other, they ended up to be matching, both 65 degrees. The same thing is true on these two angles, both 115 degrees. The same thing happened here, both 95 degrees. And then lastly here, they were both 85 degrees. That relationship is what we're calling a vertical angle relationship. So if we're looking at that diagram, we need to first define what vertical angles are. We are going to describe those as two angles across from each other when two lines intersect. So we're describing this situation of two intersecting lines, and we're talking about these angles that are across from each other, or these angles that are across from each other. So kind of like the definition of a linear pair, that just tells us how vertical angles look. But if we work on that idea a little bit farther with these examples up top, we've also noticed that there's something very specifically true about vertical angles. We're going to call that the vertical angles theorem. So if you want to actually highlight or circle or put a star, that vertical angles theorem is going to be another reason we can use when we're solving problems. If two angles are vertical angles, then they are, I'm going to use a new symbol for us today, congruent is that symbol. Congruent is a word that tells us that things are the same size and the same shape. So in terms of our algebra problems, we can think about it in the same way we would think about the word equal. But the vertical angles theorem is something we're going to use for a pretty long time, and eventually we're going to transition away from things being just equal to being more specifically congruent. So I want you to kind of have that symbol ahead of time. It's just an equal sign with a squiggle on top. It means things are the same size and the same shape. So in terms of solving problems, we can use that idea anytime we spot something in a picture that looks like the definition of vertical angles. So we have two intersecting lines right there, They intersect at point E, and we're looking at the angles that are across from each other. And so we can mark these in a way that matches to show that we're using the vertical angles theorem to solve the problem by saying the angle on the left, so that would be the measure of angle REG, has to match or is equal to the angle on the right, which would be the measure of angle AET. They must be the same size. So if we switch into algebra mode, we're going to have 13x minus 15 on one side and 10x plus 6 on the other. And then you can do your algebra to solve that equation for what x is going to equal. You should end up with x equal to 7 at the end of that solving. Do a quick geometry double check. They wanted us to solve for x, so if I could show this all on the screen at the same time, I would write x equals 7 in that answer blank at the bottom of your page. Alright, so that is now the fourth reason that we've come across in Standard 2 for solving problems dealing with angles. We have 2 more to go through, and then we'll be done with all 6, and we'll be ready to start reviewing and practicing to get ready for our assessment. Alright, that's a little bit clearer. Hopefully that helps. Our last 2 are both definitions. So if you want to highlight or star or circle and mark that these 2 are our last 2 reasons that we're going to be able to use, we will define and then we will do an example of each so that you can see how they work. Alright, first things first, the definition of complementary angles. So complementary angles are going to be 2 angles that add to a very specific amount. Some of you might already know what complementary is because sometimes they show up in a middle school math class, but 90 degrees is the amount, and they are allowed to be adjacent, which means they're allowed to look like a right angle in a picture that's been split up into 2 adjacent angles, but they don't have to be next to each other. In fact, we might not even have a picture given to us at all. We might just have information that says complementary. That's the only way we'll actually use the definition of complementary angles as a reason. If we see that word printed, then we know we're going to use the definition of that word as our reason for our work. So what our equation does is it takes the 2 angles that are complementary and it focuses on how those 2 angle measures, so the measure of angle DEF and the measure of angle LMN, would need to equal 90 degrees when added together. And you can put the degree symbol in your equation or not, that's up to you. Substituting in what they've given us, 43 was the measure of angle DEF. We're going to add to that the measure of angle LMN, 6x plus 5, and even though we can't see it in a picture, they told us the word complementary, so we know that it's going to add up to be 90 degrees. Once you do your solving, hopefully you're combining like terms. 48 plus 6x equals 90. Subtract that 48 over, 6x equals 42. So x is going to be 7. If we do a quick check, x was all we were looking for, so x equals 7 is acceptable to put into our answer blank. Our last type of problem is the definition of supplementary angles. So our final reason, the 6th one. Supplementary is going to be angles that still add up to a specific amount, but not 90 degrees like complementary. Instead, supplementary angles add up to be 180. You might be thinking, well, wait a minute, that sounds a whole lot like linear pairs. And you're right, it is very similar to a linear pair, except a linear pair must be adjacent, and supplementary angles are not necessarily adjacent. So instead of seeing a picture of a linear pair like we did up in the top in the introduction, we will see the word printed out. If we see that word printed out, just like with the word complementary, we know that what we're going to use in our problem for our reason is the definition of supplementary angles. So it's not based on what we see in a picture, like it is for vertical angles theorem or linear pair theorem. It's based on that vocabulary word and understanding that vocabulary word. Very similar general equation, though, to both complementary and linear pair theorem. We're going to take the measure of our two angles that are called supplementary. They'll be added together, just like they were with complementary, but they're equal to 180 degrees this time instead of 90. And that general equation doesn't look any different if it's a linear pair theorem problem. It's just a different reason because you're noticing it from a picture versus noticing it from a vocabulary word like we are in this one. So if we substitute our values in, the measure of angle DEF is 3x plus 2. We're going to add to that the measure of angle LMN, which is x minus 6, and together they're going to make 180 degrees since they're complementary. A little bit more to do this time with like terms, since we have x's that can be combined and constants. I'm going to add 4 to both sides, and then when we divide, x is going to turn out to be 46 for this problem. And since the instructions say find x, that can go in our answer blank. X equals 46. Now that we can see the answer blank for this one, I'll drop that down as well. X is equal to 7. All right, go ahead and flip the page and meet me back here for the examples. Okay, on the back side of in class 7, we have 5 examples to work through. Now we have finished all of the notes for standard 2, so these examples might not use only the information that we talked about today, but they might also go back and give us opportunities to practice angle addition postulate or definition of angle bisector or linear pair theorem. So we're going to be on the watch out for those, or the lookout for those, to see if any of those will help us. All right, number 1, find x in the figure below. And I notice our little symbol that shows us that we might have some complicated algebra to deal with. So all we have is the picture, which means we're not going to be using any definitions because we don't have any vocabulary words. So if I'm looking at the two angles they've given me, those angles seem like one of the kinds that we noticed in the picture at the beginning of class today. They are formed by intersecting lines and they're across from each other in that picture. So these are those vertical angles that we learned about today. And the vertical angles theorem is what gives us the information that the measure of angle REA is going to match and be equal to, or congruent was that new word that we used, the measure of angle GET. So we've got 10x minus 4 for the measure of angle REA and x squared plus 5x for the measure of angle GET. I see x squared and x's in this problem. So this is a situation where we're going to make this equation equal to 0 by moving everything on to the side where x squared is positive. Subtracting 10x and adding 4 will accomplish that. And then whatever your process is for factoring, so that we can use zero product property, you're going to need to split this into those factors, looking for numbers that multiply to be positive 4 but add to be negative 5. So it looks like negative 4 times negative 1 will multiply to be positive 4 but add to be negative 5. So then we've got x minus 4 equal to 0, which means x equals 4, or x minus 1 equals 0, so x equals 1. But we might not have a situation where both of these work in geometry. So our goal to find x is going to include popping back up to this picture and making sure that they both are reasonable geometrically. So if we start with the 4, 10 times 4 is 40, minus 4 is 36. So that angle turns out to be 36. That's an acceptable measure for an angle. If we plug in 4 here, 4 squared is 16, plus 5 times 4 is 20. 16 plus 20 is also 36. So they match, they're both positive. X equals 4 seems acceptable. Moving on to our second possible answer, if x is equal to 1, 10 times 1 is 10, minus 4 is 6. Now that seems kind of weird because this angle looks bigger than 6 degrees, but remember we don't go based on what angles look like, and 6 is positive, so that's an acceptable value for that angle, as long as this angle gives us the same result. 1 squared is 1, plus 5 times 1 is 5, 1 plus 5 is 6. So we get positive angle measures and they match, which means x equals 1 is also a possible answer. Alright, moving on to example 2, I notice a vocabulary word. So right away, that tells me I'm going to be using a definition. I just need to remember what the definition of supplementary angles tells me so that I can set up my problem with an appropriate equation. So if we think back to the definition of supplementary angles that was new today, that was where our two angles, in this case, the measure of angle APE was the first one they listed, combines together with the measure of angle EPB to give us 180 degrees total when they're supplementary. Take our 5x plus 22 to plug in for the measure of angle APE. Take our 4x plus 5 to plug in for the measure of angle EPB. And then we just have the algebra to do to figure out what x is equal to. Combining like terms should be first, but then I'm going to skip to the answer. You should end up with x equals 17 if you finish out that algebra. Pay attention. This is the first problem today where they haven't told us to find x though. So if I'm looking for the measure of angle EPB, here's my clue about what that angle's measure is going to equal. So I need to take my x of 17 and plug it in where x is located in that expression. 4 times 17 is 68, plus 5 more is 73. So the final answer here for the measure of angle EPB would be 73 degrees. On to number 3, I'm noticing something similar. We've got a vocabulary word, so I know automatically I'm going to be in definition of complementary angles mode. I just need to remember what that definition tells me so that I can write the appropriate equation. I know I'm going to take these two angles and add them together because complementary means that the angles add up to be 90 degrees. Our goal this time is to find x, so once I substitute these values in and I take care of the algebra, that x value that I get is going to be my answer for this problem. So it looks like 20x is going to be 80, so x is going to turn out to be 4 for this problem. Moving on to example 4, I don't see any vocabulary words, so I'm not in definition mode. The three options if we don't have a vocabulary word would be angle addition postulate, vertical angles theorem, or linear pair theorem. I'm seeing a line, and I'm seeing two angles that are adjacent to each other to form that straight line, not across from each other like vertical angles would be. So this is going to be a review problem from our in-class 6 notes where linear pair theorem is going to help me set up my equation. If I give this angle a name, I'm looking at the measure of angle PQR. I could have also called it the measure of angle RQP. That's going to add together with the measure of this other angle, so the measure of angle RQS, to be equal to that 180 degrees that comes from that straight line. Substitute in our values and pay attention to the fact that I'm looking for an angle on this one. So I'm not going to be able to just stop when I figure out what x is equal to. I'm going to have to keep solving to answer that question. If you go through all the algebra steps, you should land on x equal to 23. So then to finish it up, I'm looking for the measure of angle RQP. So that's going to be this x plus 42. So if we think about our x, which is 23, we're going to add 42 more onto that, which will give us the measure of angle RQP to be 65 degrees total. All right, we're almost there. One last example. Scanning through, I don't see any vocabulary words, so we're not going to be in definition mode. Again, my options are angle addition postulate, vertical angles theorem, or linear pair theorem. I don't see two intersecting lines for vertical angles theorem, and I don't see a straight line like my previous problem for linear pair theorem. So the only option I have left is angle addition postulate. Now the good news is that I see all of the required information for angle addition postulate. I have the two small angles. One of them would be the measure of angle ABD. The other one is the measure of angle DBC. And I know that those small angles will add together to form this big angle, which is the measure of angle ABC. Now this is important marking to notice. That box tells me the measure of angle ABC is 90 degrees. So some of you might be thinking, couldn't I use definition of complementary? And the answer is no, because they didn't tell us we had complementary angles. So you're not writing this equation based on your knowledge of that vocabulary word. You're writing this equation based on the fact that you see those two smaller angles added together to be a 90-degree right angle. Angle addition postulate. This one again has x squareds and x's, so I'm going to get those written next to each other and subtract this 90 over to get the equation equal to 0. This is going to be another situation where we need to go through that factoring process so that we can use our zero product property to solve. So I'm looking for things that multiply to be negative 72 and add to be positive 6. Positive 12 and negative 6 are going to be the values that will take care of that for me. So if I split this down the middle and I think about x plus 12 equal to 0, x will be negative 12. X minus 6 equal to 0, x will turn out to be 6. And my goal this time is to make sure I'm giving an angle measure as an answer. And the angle they specifically want me to focus on is angle ABD right here. So if we test out negative 12 squared plus 18, something weird is going to happen. Negative 12 squared is 144, plus 18 more, it doesn't really matter what the answer is, that's already bigger than 90 degrees. So that doesn't make sense for this geometric problem, which means x equals negative 12 is not going to be a valid answer. If we try that same thing with 6, 6 squared plus 18 is 36 plus 18. That's doable. So x equals 6 we will keep, and that gives us our answer for the measure of angle ABD. 36 plus 18 is 54. So 54 degrees will be our final answer. All right, we'll see you in class. Thanks for watching.